Continuing section 21.7 on magnetic fields produced by currents, we can also see the current that's produced when you have a loop of wire. You have wire that follows a circle. Turns out at the center of a circular loop, the magnetic field is given by this equation. Mu naught times the current divided by 2 divided by r, where this r is not just any radius, but the radius of the circle. Right? So if we imagine the loop, this is the full radius of that. And this only gives us the magnetic field at the center of the loop. It's a little more complicated elsewhere, but there are many cases where that's the most important place to know it, because that's at the center of the loop is where the magnetic field is most uniform and where you have the strongest effect. Now, how do we figure out the direction of this magnetic field? We're going to use our right-hand rule number 2 again, and we're going to put our thumb in the direction of the current, and our fingers curling around will give us the direction of the magnetic field. So if we pretend this is a coil of wire, my thumb is going to go around the loop, and then my fingers will poke through, right? And that tells me that, okay, if it's going like so, then the magnetic field will point to the left. If instead the current is flowing the other way around, then I need to reorient my hand so that my thumb is pointing that way, going around. And now my fingers are pointed to the right instead of to the left. So that gives us the direction of the magnetic field when you have a loop of wire. Now that we've seen this, let's check out an example. Example 10, finding the net magnetic field. A long straight wire carries a current of 8 amps, and a circular loop of wire carries a current of 2 amps and has a radius of 0.03 meters. Find the magnitude and direction of the magnetic field at the center of the loop. So as we look at this, we know at the center of the loop, there's going to be a magnetic field due to the loop, but also due to this long straight wire, right, which is called 1, and the loop's labeled 2. So we can figure out the direction for each of them, right? 1 we could start with is 2, the loop itself, right? And if I orient my ring so that it's similar to that, and I have my thumb wrapped around that ring, then my fingers poke down through it. So I can draw that in. If you imagine this going down below, and call that B2. Just label, maybe I'll do it on the side. B2 is going down. All right. Now what about I1? If we go to that instead, we need to again put our thumb in the direction of the current and then pay attention to the direction of the magnetic field, not at just any point around it, but specifically when we're to the right of it. So I'm sorry this is a little hard to show, but when we're to the right of it, notice the magnetic field is going up at that point. So make sure you're trying this with your own hands so that you can see that I1 is producing a magnetic field B1 going up. Both of these are creating a magnetic field, but notice the magnetic fields are in opposite directions. That means we're not going to be able to add them together because they're opposing each other. So when we want the net magnetic field, that means we are going to have to do what to show that they're in opposite directions? For the net field, we're going to have to subtract them. So if we define B1 as in the positive direction, we could say B1 minus B2. And then for each of these, we can use the equation for its given geometry. For the loop, we can use the loop equation we just saw, mu naught I over 2r, where r is going to be the radius of the circle, and then we have the current of 2 amps. And then for B1, we are going to use the current of 8 amps with that mu naught I over 2 pi r. What's the r for current 1? Well, notice because the picture shows them as right next to each other, that r distance is just going to be the radius of the circle. So we're going to use the same r for each of them. Let's see how that plays out in the calculation. Right, so we have the overall magnetic field is equal to B1, which is going up, minus B2 going down, with those equations for the line versus the loop. We could simplify it if we notice both of these have a mu naught and a 2. We could pull that out in front. That's nice because it's mu naught is a pain to type out the 4 times pi times 10 to the minus 7. So if you can do it less times, that's helpful. And then we just have current 1 divided by pi r minus current 2 divided by r. In this case, because the r's happen to be the same, you could have pulled that out as well. But when you calculate out, you come out with 1.1 times 10 to the minus 5th Tesla. And notice it is positive. Why is it positive? Well, even though this first one had an extra pi in the denominator, which is a factor of 3, this current is 4 times bigger. So that's bigger than pi. So that's going to overweigh. It's going to be stronger magnetic field due to 1 versus due to 2, due to that loop. So this highlights how we can combine two different geometries to figure things out. Now there's another useful thing to consider when you're thinking about loops of wire producing a magnetic field. And that's that the field lines around a bar magnet resemble those around the loop. So around the loop, we notice that it's going out of one end of the loop and then it wraps around, right, to the other side where it could go in. So it's really hard to show, but it's drawing these loops that go around, just like a bar magnet has loops going around on either side of it. So when you have a loop of wire, it actually behaves as though there's a bar magnet there. So you could imagine that a loop of wire is similar to having a bar magnet. It's not actually a bar magnet, but it behaves like a bar magnet, which can have some really useful properties. For one, it can help illustrate the rule of when loops will attract or repel each other. So if the currents are going in the same direction, and that means the bar magnets are also in the same direction, there's a south pole and a north pole near each other, so there's going to be an attractive force. If instead we reverse one of the currents so it's going in the opposite direction, now we effectively have two south poles next to each other, and this is going to be repulsion, where the two loops feel a force pushing away from each other. You could also again show this by using your thumb in the direction of the current, your fingers in the direction of the magnetic field, and noting that that magnetic field then acts on the charges in the other. Finally, for this section, there's one more geometry that we are interested in, and this is something known as a solenoid. This is if we take our coil, instead of just having one coil, we have a whole bunch of coils next to each other, right? We just keep wrapping them around. They get wound up. And the advantage there is that instead of just having, a single bar magnet that has these small loops around, it becomes a whole series of them, so it produces this very uniform magnetic field in the middle that is again similar to a bar magnet where there's a north end and a south end, and it's very strong, very powerful. So if you're inside the solenoid, the magnetic field is given by our constant mu naught times the number of turns per unit length times the current that is passing through the solenoid, right? Coming out of the battery, wrapping around, going out the other way. This number of turns per unit length you could think of as the number of turns n over the total length. So if it said that there were 200 turns and that it was 5 centimeters long, then you could say, oh, I'm going to divide it by 0.05 meters. And there you would have it, probably longer than 5 centimeters. But just as an example, that gives you some sense of the number of turns per unit length and how you can do calculations of the magnetic field created inside a solenoid as well. We have just one more section to go, so I hope that you will stick around for that last video.